Hi, I'm Anwar Hedar, and today I'll be presenting my CUDA Fractal Renderer project. This project combines the computational power of GPU programming with the mathematical beauty of fractals to create a high-performance, interactive visualization system. Let me take you through both the theoretical foundations and the technical implementation before we dive into a live demonstration. Fractals are mathematical objects that exhibit self-similarity at every scale. Zoom in infinitely and you'll keep finding similar patterns. But fractals are not just mathematical curiosities. They appear throughout nature. Coastlines, cloud formations, tree branching patterns, even our cardiovascular system all show fractal behavior. What makes fractals unique is their fractional dimension. They exist somewhere between traditional 1D, 2D, and 3D objects, hence the name fractal. While fractals create stunning visuals, their applications extend far beyond art. In data compression, fractal algorithms can reach ratios up to 1000 to 1 by exploiting self-similarity. Smartphone antennas often use fractal geometry to operate across multiple frequency bands in a compact space. In finance, fractal analysis helps model volatility in chaotic price movements. Medical researchers use fractal dimension analysis to distinguish between healthy and cancerous tissue. And in computer graphics, entire landscapes can be generated procedurally using fractals, thus saving massive amounts of storage. Even internet traffic follows fractal patterns, helping engineers optimize network performance. The project architecture leverages two powerful technologies. CUDA handles the computationally intensive fractal calculations, utilizing thousands of GPU cores in parallel. OpenGL provides the real-time visualization layer. The key to the system's performance is efficient interop, using direct memory transfers from CUDA to OpenGL. The system operates in two modes: a console renderer for benchmarking and batch processing, and an interactive viewer for real-time exploration. This modular design lets each component be optimized independently. The CUDA implementation assigns one thread per pixel, so at 1080p, we launch more than 2 million threads at once. Each thread independently computes the iteration for its pixel. To maximize memory bandwidth, we keep memory access coalesced. Consecutive threads read and write consecutive locations. The code provides two kernels, one which is float-based for maximum speed, and the other used double precision for deep zooming. Thread blocks are configured as 16 × 16, which gave us the best occupancy for our GPU. We also reduce warp divergence by structuring escape conditions so threads in the same warp follow similar paths. Finally, the build system auto-detects the GPU's compute capability and targets the correct architecture, from Jetson boards to Blackwell GPUs. On our GPU, which is an RTX Pro 6000 Blackwell, performance exceeded our expectations. In benchmark mode, where the GPU recomputes the fractal every frame, we measure true computational speed. At 64 iterations, we hit 900 plus frames per second, which is about 1.8 billion fractal iterations per second. At 256 iterations, we still stay above 700 FPS. Even at 2048 iterations, we remain above 240 FPS. When zoomed deep into the boundary, performance settles around 60 FPS because every pixel reaches the full iteration limit. Now it's important to separate compute FPS from display FPS. The monitor only shows 60 FPS, 60 Hz. But internally, the GPU is computing at 900 FPS. This computational headroom is what gives us zero lag, instant panning, and smooth zooming. We can zoom to about 10 to the power 14 magnification before double precision limitations appear. And an interesting result, 32 times more mathematical work only slows us down by about 4 times, thanks to early escape behavior. Finally, the 10,000 plus FPS number represents pure display throughput when reusing cached frames, confirming that memory bandwidth isn't the bottleneck. The renderer implements 4 classic fractal types: the Mandelbrot set, the Julia set, the burning ship, and the tricorn. The Mandelbrot set uses the iteration Zn plus 1 equals Zn squared plus C and is the most famous one. Julia sets use the same formula but with a fixed parameter, generating an infinite family of fractals. The burning ship fractal uses absolute values, producing sharp, ship-like structures. The tricorn use complex conjugation, giving anti-holomorphic dynamics. All 4 algorithms live in a single CUDA kernel using a switch statement, so we can swap fractal types at runtime without compilation. This maximizes code reuse while keeping performance high. The interactive viewer provides 6 color schemes, each highlighting different fractal features. Color mapping uses smooth interpolation to produce continuous gradients. The animation system cycles through color spaces, revealing hidden patterns. Navigation is intuitive: click and drag to pan, scroll to zoom, with the math handled transparently. Users can adjust iteration counts from 64 to 2048, balancing detail and performance. And Julia parameters can be changed in real time, unlocking infinite variations. Deep zooming introduces numerical challenges, so we use double precision to maintain accuracy up to 10 to the power 14 magnification. To avoid GPU timeouts, kernels are optimized to handle up to 2048 iterations per pixel, even when many threads hit that limit. Smooth interactivity required careful memory design. Our 1 thread per pixel layout gives naturally coalesced memory access. Benchmark mode makes the difference between computation and display performance very clear. 10,000 plus FPS when reusing cached frames, and 900 to 60 FPS depending on iteration count and the zoom depth. We also mitigate warp divergence with early escape checks, keeping slowdown to roughly 4 times even when the work increases 32 times. And the rendering pipeline uses direct CUDA to OpenGL transfers, chosen for stability over more aggressive zero-copy methods. Now let's see the system in action. I'll start with the classic Mandelbrot set and zoom into regions where infinite complexity emerges. Then we'll explore Julia sets with real-time parameter changes, compare single versus double precision, and experiment with different color schemes. Throughout the demo, you'll see live performance metrics showing hundreds of frames per second while computing billions of iterations. Let me switch to the live demonstration now. The make provides several options. The important one is the run viewer, which kind of consists of the bulk of the demo, and at the end we're gonna run the benchmark. Let me arrange the windows so we can see what's happening here. All right, so the top window, you have the menu and all the keystrokes appear in the top menu. The bottom, of course, is the fractal canvas, and the title of the window shows the display, which we can toggle between cached display and true frames per second, the zoom level, and the iteration. Let's start with the iteration. As you see here, plus or minus for iteration 0 and 9. So plus and minus increases or decreases the iteration by 64, as you can see. If you press 0, we have minimum iteration 64, at 9 2048. The higher the number of iteration, the more details we have and the more we can zoom throughout the fractal. So we're gonna keep it to at this level, which is the most precise level, specifically because we have a strong, a powerful GPU. All right, so if we press M, we can get the menu back again. Switching between fractals, so 1 is the Mandelbrot, which is this one. 2 is the Julia. If we are in the Julia sets, these keys apply, where we can change the shape of the Julia by using these keys. 3 is the burning ship. 4 is the tricore. Let's go back to Mandelbrot and the menu again. So we're done with the iteration, we're done with the fractals. Let's check the colors. So we have 6 different color schemes. So Q, you can see here, is grayscale, rainbow, fire, ocean, psychedelic, and electric. The psychedelic and the rainbow allow for animation, and the animation is triggered by spacebar. So let's go back to M. You can see space animate. So if I press space, the colors start changing for the W and the T. If animation is on, it doesn't affect the other scheme. Stop the animation, and let's go back to 1x. So the last thing we need to toggle is actually the benchmark mode. So if we do the B, we toggle the benchmark. This is really, it lowers the FPS, and it forces the recomputation of every single frame. So I'm gonna just move it a little bit so we can see. So now this is effectively measuring the true frame per second. And as you can hear now, I don't know if you can hear it, but the fans are on the GPU. I have like 4 fans. They're all now running at maximum speed because of these computation, which forces the GPU to crunch these numbers. Of course, if we zoom in, the FPS starts to go down, and then we can go back. And I'm not gonna keep this on. I'm gonna toggle it back to the display. And if we are in display, if you do the animation, you see that the display goes down because it can't cache it anymore. I'm gonna stop that. All right. So back to square one. So now the interesting part is actually the zooming on the of the fractal. So let's start zooming. The zoom is through a couple of things that I forgot actually. If we move the pan it either with the mouse or with the up and down, left and right arrows, we can center it back with the C. If we increase it or decrease it, we can with V we can set it back and C. And if we change, for instance, the color and we increase it and then we move it and we press X, we go back to the initial setup. All right. Having said that, let's try to zoom on this fractal. So let's zoom and notice here how the zoom magnification here. So we're gonna go and find these small thing. And every time we find something, we're gonna go to the smallest part and then zoom, and you can see the similarity. So every time we get something, and then I'm gonna zoom on this part here, the small part, and we are at what, 10 to the power roughly 10 to the power 7 here. So that's 10 million. If we press the animation, you see the start giving nice nice colors. We can switch to a different animation. We can go back to a different color. Can zoom further. We can zoom up to roughly 10 to the power 14, and you'll know where you reach the limit of the zoom because of the pixelation. So here we're starting maybe to have, here you go, we're still good here, we're still good here, here you go. This is the pixelation, so we are at 10 to the 14. So if I go back a little bit, so yeah, 10 to the 13, 10 to the 14 is the limit of the magnification. All right, so let's go back. Let's zoom out to see where we were. So I'm scrolling with the wheel. I'm zooming out with the wheel, and you can see how fluid it is. There's absolutely no flicker. And no choppiness, smooth all the way. All right, so let's do an X, and then let's find another spot and something a bit more interesting. Let's see here what we have. Yeah, absolutely mesmerizing. Some of those are really absolutely gorgeous. Let's go here. This is nice. And then we can go on the small part, and on the small, then pick a smaller one, and it just goes on and on and on. Small one. We're what, at 1 billion? Roughly 10 billion, and then we're soon gonna reach up. That's the pixelation. See how it deteriorates here. Let's see. That's roughly the limit. 10 to the 13, 10 to the 14. Between 10 to the 13, 10 to the 14 is the limit. And then we're gonna zoom back, zoom out actually. Zoom out. All right, we can do the same thing for the Julia. Let's change something interesting here. Not the menu. There you go. Same principle. Zoom in, find something next to it. Zoom back. Zoom back. Zoom more. Change color. That's nice. Okay, X. Tricon, not very interesting. I mean, if you look at this, like noise here, but it reminds me when I used to do scuba dive. For those of you who scuba dive, when you dive into water that's not clear, and you're going down, you got all these particles coming to you. This is what it reminds me of this. But there's an area here that's actually nice to see, which is roughly here. This area. I'm gonna change the color for this one. See, it looks like a temple or columns or something, which is I find it very interesting. Not as let's see if I do animation changes. Doesn't change much. Not as interesting as the others, but if you zoom in, you keep on zooming, you see all these motifs and these patterns, they keep on, you know, I find them very interesting, personally. Like, it reminds me of, you know, these old inscriptions in caves, old caves and stuff like that. Anyway, so we're here. That's the pixelation here. So that's the trichord. Let's go for the fourth fractal, which essentially is similar to the Mandelbrot, but it's like a sheared Mandelbrot, which it gives it like a topographic, like topology flair to it. Let's do some animation here. See if they find something interesting somewhere. Yeah. I mean, you can spend the whole day zooming in, zooming out, changing colors, finding hidden stuff. That's interesting. Yeah. All right. So that covers the viewer. I'm gonna press escape. And now I'm gonna run the benchmark. So benchmark will give me the block size, and there's something interesting. The block size, double and single precision, 8 by 8, 16 by 16, 32 by 32. Give some statistics. The interesting one is this one, actually. Let's copy this and paste it here. Paste. And this one, we can run. Let me run the CPU versus this argument. This gives the performance between CPU and GPU, which is on the GPU is up at 63 times faster. But then the interesting one is the animate. So if we do animate resolution, and then 1920, 1880, let's say this one. Let's hope this works. All right, so that generated a slew of images, and if we go to the repo here, they're all in the output. And the idea is, if somebody doesn't have a GPU and you want to zoom in the fractal, and just create these zoomed images. Okay. Not very interesting if you have a GPU, but it just gives an idea, you know, about the zooming effect, and also generates, you know, other images with different colors. I think I covered everything that needs to be covered. So what else can I do? Let's do a make clean and see if this works. Oops. Yep. And we go back to square one. Okay, I hope you enjoyed the demo. The demo runs on this machine, and we also compiled it on the Jetson Orin Nano, and it works also there. Of course the FPS is lower, which is normal. You can find the source code on the GitHub. It's publicly available. Download it, compile it, and play with it. Thank you for your attention. Take care. Bye-bye.